Assalamu alaikum, my dear students. Hope you will be fine and okay. Uh, I'm your teacher, Muhammad Ikram, from Pakistan International School, Taif. Today lecture is lecture number 5, Unit Electrostatics. Our today topics are area vector, electric flux through a closed surface. Although area vector is not our direct topic, but it is extremely important because for the understanding the concept of the electric flux, we need to understand the area vector first. So let us start with the name of Allah Almighty. Bismillah ar-Rahman ar-Rahim. Our topic is the area vector. That what is area vector? This is our today topic, area vector. Now let me tell you something about the area first. I already know that it is very easy for you since it is of the class 4-6 level. Area is in fact the size of an surface. The size of a surface is called it is called area, or it is the region or space bounded by the surface of an object. For example, if we have this object, and let if I mark the boundaries A, B, C, D, then what is the area? The area is in fact what? It is in fact the region bounded by this closed path A, B, C, D. This is called the area, right? We have two kinds of areas, the flat area or the open area. The open area, and we have the area for the closed surface, right? So better if I would write open surface rather than area. We have two kind of surfaces, the open surface and the closed surface. This is the open surface, this is the open surface, this one is open surface, this one is open surface, this is open, this is open, this surface is open. However, the surface, this is called the closed surface. For the cube 3D surfaces, the sphere, this is called the closed surface, right? Now as you see in the previous classes, you consider the area as a scalar quantity. Area being what? The scalar quantity, that only the magnitude work best for those things. But in electrodynamics, area is controversial. It is not considered a scalar, rather it is considered as what? Is a vector quantity. Why? Because for electrodynamics, the top surface acts in a different way than a bottom surface. This is why we call it what? A vector quantity. For example, look at this object. Here you have, if I just draw a shape like a 3D shape, for example, see here, I'm drawing a 3D shape as you see. Look, if I just label this as the y axis for the two-dimensional plane, then you see that look, the top surface points in the top surface point in the positive x-axis, while the downward surface points in the negative x-axis direction. So this is why these two are not the same. The top surface different than the bottom surface, though they may be the same in magnitude, but they are pointing in a different direction. This is why we need to define what? We need to define the area vector. So what is the area vector? Area vector A is defined to be the magnitude of the area bounded by a certain surface into a unit vector, right? Now this unit vector is in fact what? Direction specifier. Direction specifier. And since this is the magnitude, therefore it turns it into the area vector. Now let us see how. The question is that how we can give directions to a particular surface area, right? We do this by using the right hand principle. If you apply the right hand principle, then according to the right hand rules, that if I consider this plane area like this area, if I consider this area as you see like this area is the plane area along the x-axis, then according to the right hand rule, if the curl finger shows the bounded area, for example, if I might curl my finger in the direction A specified by this orange pen like this, then the thumb always point up, right? So what does this means? That the area vector for the blue, this area vector will be along the positive y direction, right? So for this plane, it is always by using what? The right hand rule, we can specify the direction for the area vector by using the right hand rule. Similarly, you can apply it to this also, and the direction of this area vector will be, if the area vector A here is equal what? The area bounded by this rectangle into the unit vector, and this is the unit vector in the positive direction, right? We can do this for in the horizontal direction also. Similarly, you can do it for this, you can do it for this, for this, for this. However, for the open surface like this is not a regular object, so you will divide this object into area elements as you see the small area elements, the small pages. Since area vector is always perpendicular to the surface area, to the plane of the surface, so here the area vector will be a1, here the area vector will be a2, like this one. Similarly for this, for example, if I use it the magnitude, so the area and the n vector, I can do it like this way also for this, right? So the area vector A will be n into the magnitude of that area vector, the small length element, right? And later on for the total area, you can just add area a1, a2, a3, a4 like that. Okay, these are for the open surfaces, right? For the closed surface like this, what will be the area vector? So for the closed surface, for the top, you have the area vector, for example a1 pointing along the vertical direction. For this, it will be like this area vector a2. For this, it will be area vector a3, and similarly for the other three surfaces. For this surface, right, for the spherical surfaces, for all spherical, cylindrical and cubical surfaces, all these surfaces, we call them the closed surface. For the closed surface, area vector is always outward, is always what? Is always outward, right? So you see it here, for example, look here. For this, I'm coming to that point, but for this surface a1, this surface a2, right? These are the flat surfaces, flat surface. But here we have the curved surface also. This is which surface? The curved surface. The curved surface. For the curved surface, we have what? This is the area vector A for curved surface, right? So you see here in all the cases that the area vector can be drawn and the magnitude of any area vector can be found by n into in a unit vector and the multiply by the magnitude. For this kind of surfaces, what we will do, we will divide this into again into small pages, just like you have seen on the football. So like this, like this. So each area A1, A2, A3, A4 like this. So to draw the area vector for these shapes, what you will do? For this, area vector will be this one. Here area vector will be this one. Here the area vector will be this one, A2. Here the area vector will be this one. Must be perpendicular to the plane or to the surface, right? Area vector will always be like this. So this is all for what? This is all for the area vector. Similarly, for this, what you will do, you have this, you have this, and you have this, like this one. Is it clear? So this is for all the area vector. So area vector is very, very important uh, physical quantity. In electrodynamics, area is considered to be a vector quantity. Why? The up surface is acts in a different direction than a downward surface. Similarly, the rightward surface acts in a different direction than the leftward surfaces. Now, our next topic is the electric flux. Electric flux. Electric flux denoted by pi. This is very important term, right? Now, once when I define the electric flux, then I will switch over back to the concept of the electric flux, that what is in fact the electric flux is. Electric flux can be defined as the electric field lines passing through a unit area, passing through a unit area of an object, yeah, through a unit area held perpendicular to the direction of electric field lines. Electric field lines are simply, you can say, electric lines of force passing through a certain area is called the electric field lines, but this does not give a very good concept. Physically, we can define this as it is the dot product. It is the dot product of the electric field intensity E and area vector A. Mathematically, we can write it as the electric flux is denoted by pi, and it can be written as E dot A. Moreover, we can write electric flux as E A cos theta. Now, what is this theta? It is what? It is the angle between the electric field intensity and the area vector A, right? That is the electric flux. So if I just mark this, look, then what will be this thing? It is the projection of the area vector in the direction of the electric field intensity. So electric flux being the scalar or the dot product. So this is always what? Naturally, it is a scalar quantity. It is a scalar quantity. And what will be its SI unit? The SI unit, the SI unit of this electric flux is what? Look, what is the unit of this? That is Newton per coulomb. And what is the unit of this? That is the area meter square. So Newton meter square per coulomb. It is the SI unit and it is important. The SI unit. Now this electric flux, there are many important points which I want to explain. One, your electric flux may be positive, the electric flux may be negative, sorry, zero, and the electric flux may be negative also, right? We will apply the idea or the concept of the electric flux to open surface as well as to the closed surface, right? But mostly whether if the surface is open or whether if it is closed, in all the case electric flux is very important. Now what is the importance or the concept of the electric flux? You know that I'm always interested in the concept rather than just going mathematical. What is the concept? The concept of the electric flux is extremely important. That is, by knowing the electric flux, by knowing what? By knowing the electric flux, we can calculate the electric field intensity. The electric field intensity at a point due to any charge distribution. Due to what? Due to any charge distribution. Now, this is extremely important point. The point is what? This point is very, very important point. This one. Why it is very important point? Because of the fact that you know that how much it was difficult. If you just see your one example and numerical in your the textbook, how was it difficult to apply the Coulomb's law to calculate the electrostatic force of attraction or repulsion when there were more than two charges? For the three charges, what a long way you went. So that is so difficult. So what if instead of a single charge, two charges or three charges, if there is charge distribution? For example, instead of a point charge, if you have a sheet of charge, if you have a cylindrical shape of charge particle, for example, a charge conductor, then will it be easy to calculate the electric field intensity of the Coulomb's law to apply? Certainly not. Very difficult. Why? Because of that vector nature. Here the electric flux is all purely what? It is purely a scalar quantity. So we can use the concept of the electric flux to calculate the electric field intensity. Once you calculate the electric field intensity, then you can easily calculate the Coulomb force for any sort of charge distribution. So this is one of the basic concept behind the electric flux. Now, the electric flux for what? For open surfaces. Electric flux for the open, yeah, due to the open surfaces. You see that in the red, we have here the electric field intensities. As you see the electric field, this is just all a single electric field, right? And this is what, these are the surfaces. Now, if I just draw the shapes using the green pen, you see, look, you see, look, see here, draw again shapes, this shape, and let me just do this here. Just do it here. And similarly, for this one, like this, as you see it. Now you just look, we have the flat surfaces. If you see, if I just label this as the x-axis, this is the y-axis, then you see that, look, in the first cases, whatsoever is the situation, the electric flux is always EA cos theta. So we have the case A, we have the case B, and we have the case C. For the case A, you see that the plane of the area, this is the plane of the area, right? The plane of the area is perpendicular to what? The plane of the area is perpendicular to the electric field lines. And if you see, look, what is the area vector? The area vector is in this direction. This is the area vector. Why? Because it is perpendicular to the surface, right? So you see that, look, in this situation, what is the electric flux? Your electric flux is maximum. Why? Because theta is what? 0 degree, the angle between E and A. And your this electric flux, this electric flux, the electric flux is EA. Why? Because cos of 0 is equal to 1. So that is maximum. So when the flux is maximum for the flat surface, the flux is maximum when theta is 0. That is when area vector is parallel to E, right? And when the flux at a certain angle, in this case, it will lie between 0 and maximum, right? And what happens in this case? The area, look at the flat area, the plane of the area is along the x-axis, and the area vector is what? The area vector is perpendicular. The area vector, you see, it is what? It is perpendicular to the electric lines of force. So here theta is 90 degree. And what will happen? The flux is what? The flux is 0 in this case. So in this case, the electric flux is 0. Why? Because theta is 90, cos of 90 is 0. Here the electric flux lies between, that is, it is greater than or equal to, for example, for the that sort of value of theta, that it lies between equal or less than maximum and less than 0 for this case. Here the electric flux is all maximum. It is maximum. Similarly, this is when the area vector is not perpendicular to the electric field line. So this is for any angle, right? Now that is the electric flux through the open surface. What will be the electric flux through a closed surface? Electric flux through a closed surface. How the electric flux through a closed surface can be calculated. This is a closed surface. For example, if you have any charge distribution, then look the electric flux through a closed surface. First of all, you have to find out the area vector. Here you have what? One, this surface is the area vector A1. Here you have this, the area vector A2. Here you have this, the area vector outward always A3. And here you have what? The area vector A4. So you have how many surfaces? You have four surfaces. You have six surfaces. One, this surface as you see, and one you have that surface, these vertical surfaces, left right vertical surfaces, top bottom vertical surfaces, and back and front vertical surfaces like that one. So you have actually the six surfaces. For example, the other one will go that way, this one will go this way, like this. Let us suppose, for example, if you have a positive charge that lies inside this, then what will be the electric flux? So you see, look, you have all, that is, this is the electric field intensity. So you see that the flux is flowing outward. So an outward flux is taken positive. Flux outward is what? Is positive. Outward flux is what? It is positive when it encloses a flux. Now let us see another case. That another case is, for example, if I just draw this box like this one as you see, and if it bounds a negative charge, for example, charge is being negative, then what happens for the negative charge? The electric field lines always points towards the charge as you see. Then what is going to happen? And if you just draw the area vector, this is the area vector, this is the area vector, this is the area vector, and this is the area vector. So if you just see, look, the flux is what? Here the flux is negative for the inward flux, that is, inward flux is taken, it is the inward flux through a closed surface is always negative, is always negative. Why the inward flux is negative? It is because of the case that, look, what happens? You have here the area vector and you have here the electric field intensity, this one, the green. Better to do that so that you can understand by colors. A, and here you have this is E. This is E. And you see, look, what is this angle? 180 degree. And you see what is electric flux? EA cos theta. So cos of 180 is always minus, so EA. So flux is negative. So flux that is flowing inward is taken as negative when a closed surface bound a charge. That is, look, flux through the outside charge distribution. Flux through the outside charge distribution. Outside charge distribution. Let us see this as a special case. Now what is that special case? For example, let us look. If we have the box, right? And if this box encloses no charge, right? The charge distribution, look, we have 5 coulomb of positive charge, uh, positive charge, 5 coulomb Q charge distribution. So you see what is the electric flux due to this charge distribution. So due to this charge distribution, the electric flux E is 0. Why? What is the reason? The reason is charge distribution lies outside the closed surface. So the flux through the surface is zero, and it must be zero. Why? Because if you just consider this face of the this face and this face, and we only consider the electric field lines along the x-axis only. Now what happens if you just find the area vector? Here the area vector is this, and here the area vector is this. So here the electric field lines and the area vector. So at this point there is the electric flux is negative, but at this point the electric flux is positive, since both surfaces are the same in magnitude. So what is the total electric flux? If I just label that surface E1 and A2, so the total electric flux due to surface what? Electric flux through A1 plus electric flux due to surface A2. So this electric flux, they are the same in magnitude, right? Look, but here the flux is what? Here the flux is negative. So it will be minus EA, and here the flux is positive. So it will be plus EA, right? And for both the area vector is the same. Here the area vector is the same area. Magnitude of the area same, electric field intensity the same. We consider only along the x-axis. So what is the total flux? That is zero. Now another special case I would like to tell you. For example, if you have this box, right, as you see, and if this box encloses positive charge of 1 coulomb, let us say, and a negative charge of say 1 coulomb, Q1 and Q2. Like this is also, for example, 1 coulomb, and this is a minus 1 coulomb of charge and plus 1 coulomb of charge. So what will be the electric flux through this surface? The net electric flux through the surface is again zero. Why? Because the flux that in leaving is the same as the flux that enters, right? So that is why the electric flux through the same and charge distribution having the same magnitude but opposite sign, the electric flux through the closed surface will be what? The electric flux through the closed surface will be zero. So that is our today topic. So what is the conclusion of the result? The conclusion of our today lecture is that area is considered as a vector quantity. Considered as a vector quantity in electrodynamics. Why the up area is different than the down area in direction. Second, we studied the electric flux, and we say that electric flux is equal E dot A or E A cos theta when they do not, that when E and A do not lie along the same direction, right? And then we apply this to open surface, and we did this for the closed surface also, right? And then we studied various cases, and what is the result? That is, if the important result, if we can calculate E, if E is known due to any charge distribution, C, I say charge distribution, right? That is, if the charges are more than 5 or 6, to which we cannot apply the Coulomb law directly, we can what? We can calculate the Coulomb's force for such situation in a very easy manner. So hope you have learned from this today topic. I just want to give you the sign of the kind of assignment here for you. Your assignment is, let us see your assignment. This is your home assignment, okay? The assignment is that, look, we have this closed surface, right? And we have the electric field, right? That is the dimension of the surface is, this is 5 centimeter, this is 10 centimeter. Okay, 5 and 10 centimeter, we have this one, right? It encloses a charge, a plus 5 coulomb charge inside it. Okay, that is the charge. This is also 10, this is also 10 centimeter. The charge is at the center. What lies at the center? The charge lies what? At the center, 5 coulomb of charge. Then calculate, that is, I will give you, this is point A. The electric field E lies along the x-axis purely. That is, we only consider this along the x-axis only, right? This is E. Then calculate number one, E at the point A, electric field intensity at the point A. Number two, electric flux through the surface. This is, look, I will be just labeling this as, and I label this as, let me just do this. This is surface A1 and this is surface A2. Calculate electric flux, calculate electric flux through the surface A1 and A2. Note it, I am telling you again, remember, note, E is only along x-axis. Okay, this is your home assignment, and thank you very much for joining my today class.